Let us discuss the different theorem that we could use in simplifying our equation. Let's start with theorem number 1, idempotency. So a plus a is equal to a added to a is equal to a. So it means that or to itself is equal to itself. Added to itself is equivalent to itself. Even if we have lots of a here, added to a, lots of a's or to a, it will just be equivalent to just one a. Okay, so that's theorem 1. Theorem 2, null element. So the effect of 0 and 1. So a or to 1 is equal to 1. Second form, a added to 0 is equal to 0. So form A is basically based on or operation. We all know that as long as there is 1 as input, the output is 1. And form B is based on AND operator. As long as there is a 0 input, the output is 0. Okay? Theorem number 3, involution or double negation. Not of A is basically A. So we are canceling the negation. So that's the meaning of theorem 3. Theorem 4, absorption. A plus AB is equal to A added to A plus B is equal to A. So how could we determine when to use theorem number 4? So it involves two terms, number of variables not equal. So like in form A, we have 1, we have 2 here, and there should be a common variable. So we have a common variable, which is A. The common variable will be the simplified version of the equation. Okay, so again, two terms not equal in size and must have common variable, and the common variable will be the simplified version of the equation. So for example, x plus y or to x plus y z. Okay, so by the way, A is not it can represent a variable or a term. Okay, so to answer this, let A equivalent to x plus y and B is equal to z. So by substitution, so replace A and B, replace x, y, and z by A and B. So we have A plus AB. This is the same as form A, so therefore this is equivalent to A. Then the answer is x plus y. Okay, that's form A. Another example, AB naught added to AB naught or to B naught C. Do we have a common variable? Yes, AB naught. Okay, in these two terms, do we have the same number of variables? No. One is 2, one is 3. Okay, so therefore we could implement theorem number 4. So just to prove that we could implement theorem number 4, so let A B naught, let B naught C. Substitute, we have A added to A plus B, the same as form B. So therefore, it is equivalent to A. And we all know what is A B naught. So that will be our answer. Okay. To prove that theorem 4 is correct, okay, so A plus AB. Using distributive law, we're going to factor out A. Okay, so we have A added to 1 plus B. And we all know that 1 plus B, based on theorem number 2, it is equivalent to 1. And anything added to 1 is equivalent to A. okay, based on postulate number 2. And A ANDed to A plus B using distributive law, we have AA plus AB, and we all know that AA is the same as A. Okay, so we have A plus AB based on theorem number 1. And if you can see, this equation is the same as form A. So therefore, A ANDed A plus B is equivalent to A. Okay, theorem number 5. This is different from theorem number 4. Theorem number 4 has common, but in theorem number 5, there are variables complement each other. Okay, so we have A plus A not B is equal to A plus B. Second form, A ANDed to A naught plus B is equal to AB. Okay, so how could we determine if theorem 5 is, we can implement theorem number 5. So it should be 2 terms. Number of variables not equal, same as theorem number 4. And there are some variables complement each other. So this is the difference between theorem 4 and 5. Complement variable in theorem number 5. So we have A. On the second term, we have the complement version, which is A naught. So therefore, theorem 5 could be implemented. A and the complement version is on the other term, which is A naught. Therefore, we could implement theorem number 5. Okay? So for example, we have B plus AB naught, C naught, D. So B will be our A, AC naught D will be our B. Substitute, we have A plus A naught B. Therefore, the result will be A plus B. So let's retrieve the original equation. We have B plus AC naught D. So this will be our answer. This is the simplified version of the given equation. Another example, x plus y ANDed to x plus y not the whole expression plus z. Okay, so let A, x plus y, and B equal to z. So substitute. So we have A ANDed to A naught plus B, second form. So therefore, we have AB. And then the final answer will be x plus y ANDed to z. So that will be our answer. And that's how we implement theorem number 5. And to prove that theorem 5 is correct, okay, so let's manipulate form A first. A plus A naught B, using distributive law, okay, we're going to get a factor form. So we have A plus A naught ANDed to A plus B. And we all know that A plus A naught is equivalent to 1 based on P6, postulate 6. And anything ANDed to 1 based on P2 is equivalent to itself, which is A plus B. And this is the same as the right side of the given theorem for form 1. Okay, so let's proceed with form 2. A ANDed to A naught plus B. Using distributive law, distribute A. So we have A naught plus AB, and we all know that A naught is equivalent to 0 based on P6. And anything or to 0 based on postulate 2, the result will be itself, which is AB, which is the same as the right side of theorem number 5. So therefore, theorem number 5 is correct. Okay? So on the next video lecture, I'm going to discuss the last 3 theorems. So thank you for listening. See you on the next video lecture.